So hi everyone. This talk is about combining Ghost and Casper, and I'll explain what those things mean. I'm Zhang, a mathematician at SJSU, and this was a joint project with Vitalik Buterin and Danny Ryan from the Ethereum Foundation. And the other 7 names on this slide are Diego, Thor, Kim, George, Juan, Juhuk, and Ying. And they were a team of undergrad and master's students at my university that I work with. And this project is about 1 year old. Disclaimer before I start is like, I'm a mathematician by training, so there's a lot of blockchain stuff I don't know. So I'll be always happy to learn more as you guys point out stuff or send me stuff with questions after the talk. Okay, so on the Ethereum 2.0 beacon chain, as all other blockchains, a set of validators, like users, want to form a consensus history. The fact that this is a beacon chain is not that important to this talk. The beacon chain has to do with the sharding design of Ethereum. For us, we can just think of this as any arbitrary blockchain. And the stuff in this talk should apply to an arbitrary proof of stake blockchain. So validators will broadcast messages, which are blocks, and attestations. We'll explain what those things mean later over the network. And each validator has their own view, which is the possibly incomplete history of which messages they saw. So just as a picture of this, if this was like the God's eye view, you mean like what actually happened in the world, where A, B, C, D, and E are blocks, and these circles are attestations, which I haven't explained yet, but roughly speaking, you can think of them as votes for the blocks before them. So, you know, someone wrote a block A, and then 6 people voted for A, and then block B, etc. But what happens with validator views is because of latency and things like this, you all know, because, you know, it's blockchain, maybe one person only sees like the blocks on the left, maybe one person only sees the blocks on the right, and another person just sees some like fragmented version with some blocks missing and attestations missing. And this is like the fundamental problem that consensus is supposed to solve. So since the views can be out of sync and stuff, we need like 2 things to get this to work. One, we need a finality rule that tells a view which blocks are final. So when you're looking at your view, even though it could be broken, you would like some guarantees based on what you think that allows you to think of certain blocks as final. So the 2 properties we kind of want are safety, which means you never finalize conflicting or forked blocks, and liveness, which is you can always create and finalize new blocks. So just to be clear, in this picture, what we're saying is we want to define certain blocks as final. So maybe we call them purple, okay? So we want to say, given a view, I can label certain blocks as purple such that we never get 2 purple blocks that are in conflict, meaning like this 4 and 4 over here, although it's fine if you fork off to this 3 in the middle, because we never mark that as final, so it's okay. And the liveness means we can just keep building blocks on the right. So if we have both of these conditions, we get to grow a chain of finalized blocks as our consensus history. And the fact that the purple blocks form a chain just comes from this safety assumption that you never finalize conflicting blocks. So you never make 2 blocks such that neither of which is a parent of the other. And as a result, you get a chain. And to help us do this finality rule, we would also need a 4 choice rule, which means you're a validator, you see a view, you're asked to build a block, where do you build it? This is a very old and common question in blockchain. So talking more about the 4 choice rule, which, as I said, is a function that takes a view as input and outputs what it thinks of as the canonical chain ending in the leaf block. The most common example for this that you might recognize from Bitcoin would be the longest chain rule, even though, of course, Bitcoin actually uses a variant of the longest chain rule, which is kind of like the heaviest weight rule. Well, like mostly it's just, is the chain long? If so, build on it. So given this view, which has a bunch of forks in it, maybe the validators, well, in Bitcoin's case, miners, will look at this and be like, well, the top thing has 6 blocks, so let's build on that. Okay. So the 4 choice rule we'll use, and the design choices here, I'm going to kind of push under the rug because you need to think about certain things when you go from proof of work to proof of stake for Ethereum 2.0, is the LMD ghost. So LMD ghost is based on ghost, the greediest, heaviest observed subtree choice rule. And this was designed by Sokolimsky and Zohar in 2015. And Vlad Zamfir helped adapt this to Ethereum in 2017 as LMD Ghost. So the LMD is the latest message driven. And this rule tells validators to follow the fork with the most latest messages attached to blocks. I'll show what that means in a picture in a second. But first of all, here's the formal thing, just to make the slide look a little bit formal. It's going to give no information, so let's jump to the pictures. So what is this LMD Ghost? So in our case, let's say we have 7 validators, and because there's 7 validators and we only care about their latest messages, which are these attestations, these little circles with smiley faces on them, that means at any given time in your view, there's 7 markers of kind of the last thing they voted for, the latest message. And then the way you decide the fork choice rule is you start the Genesis block, you move to the right, and anytime there is a fork and you don't know which one to go down, you go down the one with the most number of latest attestations on it. So in this example, notice I cleverly drew the example to be the same graph as the previous one with the longest chain. But here, because there's so much weight on this block here with 4 attestations on it, the fork is going to go down and you're going to end up inside this chain, which is a little bit shorter but has more attestations on it. And notice I split this picture into 2 for the following reason. In our rules, we have to both make blocks and attest to blocks, and we use the same rule. So if you're attesting, you attest to this best block, and if you're proposing, then you make a block on top of that block, and so forth. So whereas in Bitcoin or something, there's no concept of attestation, there's just building, so you just kind of build on the best block. So this gives us kind of a toy protocol to start, and then hopefully this picture will kind of show what this protocol roughly looks like. The slots are the most basic unit of time. In reality, they're going to be about 6 seconds, and each slot is assigned a single validator as block proposer. So you should think of slot as just like roughly each slot based on time, you'll see 1 block on the blockchain. And an epoch is a length of a constant number, and it's going to end up being 64 slots, during which each validator will attest once. In our toy picture here, there's only 3 slots per blocks, 3 slots per epoch. So, but in reality, there's going to be 64. Each validator is assigned to 1 slot per epoch as an attester. And the beginning of each slot, the block proposer makes a block. And in the middle of each slot, the attester validators assigned to that slot attest with kind of the LMD ghost rule that we talked about. So just looking at a picture up top real quick, you can kind of see how on the left, there is a kind of an ideal execution, which is first slot, someone makes a block, then maybe 2 people are assigned to that slot, they vote on it, and now everyone knows it's the best block. In the second slot, someone makes another block, 2 people vote on it. In the third block, someone makes another block, 2 people vote on it, happy, and we keep going. And then there's a fork that happens in the second epoch and so forth. But every slot, you make a block, and people assigned to the slot vote on it. And this is kind of like the toy protocol induced by LMD Ghost. So now what we're going to do, and the thing that makes this paper called Gasper, is we add this finalization rule, which is Casper FFG, to our fork choice rule, LMD Ghost. Remember, LMD Ghost just tells you kind of like what's the best chain to go down, but it doesn't tell you which blocks to consider as final. We need something from consensus for that, and that's this new addition called Casper. So we call this thing Gasper because it combined Casper and fork choice rule. And yes, to all you sharp-eyed people, in this picture that we drew, Gasper starts with GH, but everywhere else I say Gasper without the H. That's just the way it is, and I'm too lazy to go back and unphotoshop this. So you're stuck with something unprofessional. Not that we're trademarking this anyway. But what is Casper? So Casper FFG, the FFG stands for Friendly Finality Gadget. This was written by Buterin and Griffith in 2017, and it's a consensus finalization gadget that can be used on top of a blockchain. So it's not a complete consensus protocol. What it is you already have some blockchain, and on top of that, we're just going to define certain things that's being finalized, which was kind of like the point on my first slide, which is we have all these blocks. So we're going to paint some of the blocks purple so they form a chain. And Casper FFG is the thing that tells us which blocks we get to paint purple. Okay. So this protocol introduces the idea of checkpoints, which matches very nicely with our previous idea of epochs, which is every so often when you have some blocks, we're going to create like a checkpoint block, and it's like a special block, and it's the special blocks that are sometimes painted purple and sometimes that are not. So in this picture, and the way it changes our toy protocol is, it's going to be hard to explain all this detail in the time I have, so I hope you'll just kind of see the big picture, is an attestation is no longer just pointing to a block. An attestation is a vote that tells you, hey, I want to go from this checkpoint to this other checkpoint. So if you look at these little happy faces, they have two dotted lines. So each of them you can think of as this happy face is not just attesting to the later block is pointed to, but it's really voting for a transition. It says, I vote for the transition from this block to this other block. And what happens is we would say a block is justified, a checkpoint block actually, is justified by another one if more than 2/3 of the attestations in an epoch go from the first checkpoint block to the second one. And if a block becomes justified and it justifies something else that's adjacent to it, it becomes finalized. So just quickly wrapping up the intuition of that, if lots of people agreed that it was correct to go from someone else to you, and then lots of people agree it was that the next good transition is you going to someone else adjacent to you, then you become finalized and we paint you purple. So I can talk a little bit more about that later, but right now we should think about kind of how this plays in with proof of stake. And the way that works is in proof of stake, we don't have this work stuff, so we need something else. And we essentially have like a punishing mechanism, which is called slashing, that creates an incentive for people to follow the protocol. So basically in the FFG paper, it defines the following two slashing conditions. I won't go into them, even though I'll put them here. The first one is just like, you cannot make two distinct attestations in the same epoch. And the second one's a little bit hard to explain. But one, these are conditions where if you're an honest validator, you should never break. You will never break. So if you're following instructions, you'll never break these things. And the second condition looks something like this, which is you can't attest like two pairs of transactions such that one nests the other one. There's mathematical reasons why you want to do that, but if you trust me that the math works out, basically, if you do these things, if you're honest, you will not get caught. But the beautiful output is if we don't catch a lot of people, then we have finality. And I can talk a little bit about what that theorem will look like later. But right now, I'm just going to go to the next thing, which is, okay, and we need one more thing, which is, since we're combining these two things, we need to update the fork choice rule a little bit. Remember, originally the fork choice rule was just LMD ghost. So it doesn't know anything about checkpoints or finalization and whatever. And the most naive thing you can do is, let's take the last block that is justified or finalized, start from there and run LMD ghost. And this essentially is what happens, except this doesn't quite work. There are things that break around the edges, and you have to fix that. I'm not going to go into kind of the technical details on this slide because that will take forever, but I just want to say there is some blood, sweat, and tears involved in making things work kind of like completely carefully and formally, and that's the details are left to the paper. But now I get to go back to tell you what these slashing conditions do. Suppose you do have this good fork choice rule, then you kind of recover the following two theorems from the Casper paper. One is, given any view, if you have kind of like two conflicting blocks, I say pairs, that's just a technicality. When I say pairs, you can think of as blocks. If two blocks conflict, then we have enough evidence to slash at least 1/3 of the validators. So another way to put it is, if you think more than 2/3 of your users by stake are honest, then this will never happen. The other theorem, kind of also from Casper FFG, is called plausible liveness, which is, again, if you 2/3 stakes worth of people are honest, then we can always finalize new blocks, and we'll never be stuck. Like, it's always plausible that we can build more blocks on top of that. I am pushing some honest work under the rug, but I just want to admit, I think the core proofs are unchanged from Casper FFG, so I'm not gonna like really take a bunch of credit for anything new, even though we do have to prove it in a new language and there's a little bit of technical work. The interesting new thing in our paper, I think, is this concept called probabilistic liveness. And that means the following. In plausible liveness, we're just saying, suppose people are honest, then with no assumptions, we should at least plausibly be able to make new blocks and the chain can plausibly continue. However, there's like something you care about, which is like in real life, we can assume things. Like maybe there's some synchrony conditions. People do get messages roughly on time. During usual operation, even though people are maybe malicious or adversarial, how live are we? Like, what's the speed at which we can generate new blocks, justify them, and finalize them? So that's kind of the probabilistic liveness, and that was not in the original Casper paper. So I think the biggest mathematically difficult part of the Gasper paper is really trying to attack this, and it is quite difficult. So like the setup is a little bit complicated. So I'm going to try to start with something simple. So to kind of demonstrate how probabilistic liveness may work in one epoch, let's just start by talking about the first slot. And this is a mini game that I call the equivocation game. So it's something like this. You have some honest validators and some dishonest validators. Suppose you have two options, blocks A and B. And kind of like LMD Ghost, let's say the game takes place over one slot of time. And what you're supposed to do is in the middle, time 0.5, everybody is supposed to vote for the option with a majority of votes. Now let's think about what someone who's attacking finality would do to this blockchain. The bad guys, their goal is to make sure that nothing gets 2/3 of the votes, because then we're stuck in this situation where no one ever gets 2/3, and then nothing gets justified and nothing gets finalized. So that's what attacking the consensus portion will look like. This means the honest validators win if either A or B gets at least 2/3 of the votes. But the dishonest validators win if like you kind of stay in the middle area. So this should be a little bit counterintuitive. It's like, well, why is it bad if you're in the middle? And it's because, well, if the dishonest validators confuse you too much and you vote for the other block, then too many people agree on the other block, and then we can form consensus on the other block too. So winning is like at the extremes and losing is kind of at the middle. And you can kind of imagine why something like this is not completely obvious. So here's a hypothetical scenario. If the honest people are supposed to vote at the middle of a slot, and the dishonest people who don't have to listen to you somehow know that the network latency was about 0.3 seconds, then what they can do something like this. They can all vote around 0.2 seconds, 0.2 slots, sorry. And then so by the time you're voting in the middle, you kind of see this cloud of mixed votes. And it's, in the worst case, what you'll do is you basically have to flip a coin because you don't know because you might see that block A is ahead and someone else might see block B is ahead. And in the worst case, each person's an independent coin flip, even though the independence is a very strong assumption. And then, so all the honest people in the middle will be flipping coins. If this is true, then you're going to end up in a case where you get 50-50 votes. So, and then my students ran, some simulations, and under different regimes, you'll see the probability that the vote gets split can be high or very low. It's actually usually very low, but if you time it really well and have a very coordinated attacker, it is possible to split the vote. So, there's just something about winning this equivocation game that needs to be solved as a sub-problem because it really emulates the first slot. So what happens in the rest of the epoch? And I want to skim over some kind of mathematical details, but suppose you assume that the average number of Byzantine validators in each slot is epsilon less than the amount you're supposed to have, like S/3 in the worst case. Then if you set up the following events, which I'll now go into details, these events roughly mean that kind of the number of honest validators for suppose a test in each slot is at least the 2/3 that you expect. You can bound all of these things with kind of this concentration inequality, the Hofstadter's inequality, and you'll realize the probability that all these things are satisfied is about 1 minus something that's exponentially small. And so that brings us to our justification Liveness theorem. And this is why I didn't leave with it, because there's a bunch of words. But basically, the words here say, suppose we have some nice synchrony assumptions. Suppose we win the equivocation game with probability R. Remember, the equivocation game means in the first slot, some block comes out ahead and is not equivocated by kind of adversaries. Then with very high probability, basically around R, you will justify the block in this epoch. And then you can kind of see that even if we assume something really pessimistic, like 0.71 probability of having the first slot go well, it translates, at least under these conditions, to about a 68% chance, which is only loss of a 3% of justifying after the whole epoch is over. So that's kind of like what this theorem is, because it really depends on this probability of winning the first slot. And then finally, remember the way justification works, which is if you justify 2 checkpoints in a row, then you finalize the earlier one. So the probability of not finalizing a block in n epochs is the following combinatorics problem that some of you guys might have seen in like a discrete math class, which is if we color a bunch of balls red or blue, red means we justified and blue means we don't. Well, remember, we get finalization, we have 2 justifications in a row. So if we have 2 red balls in a row, that is good. So I'm just asking, hey, if we just paint these balls randomly, what's the probability that we do or do not get 2 red balls in a row somewhere? And if you look at this form, you realize you can, ignoring the 1 minus p part, this thing on the top is like this weird adding binomial coefficients where the top decreases by 1, but the bottom increases by 1. This is actually a Fibonacci number of all things. So if you can bound this whole thing by a thing that roughly looks like this Fibonacci number with an extra power of 2. And the main important thing here is 1 plus square root of 5 over 4 is less than 1. So half of the golden ratio is less than 1. And because this is true as n gets big, the probability goes to 0, which means when we do have our setup, thanks to the weird fact that the golden ratio is less than 2, we do get probability going to 1 of finalization happening after we get to n slots. So this is a computation one of my students did because she doesn't trust me. So it's really good to have students that don't trust you, because then they'll just like do a computation to make sure that you were right or wrong in the first place. So she didn't believe this. So then she was like, okay, if the justification probability is 0.68, what's the probability of not finalizing in even 10 epochs? And it turns out to be not finalizing is like 2%. So finalization was like 98%, and that's quite good. So the summary of the last things, because I know that was kind of a little bit heavy, is in an epoch, a block in the first slot is likely to get a lot of attestations with some probability R. And we kind of black box this computation of R, and that's kind of the structure of the proofs. If R is high, then the block is likely to be justified in an epoch with some probability P. And if P is high, then it's likely for the block to be finalized in a sequence of n epochs as n gets large. And that was kind of the Fibonacci number argument. So if you combine all those things, you'll kind of get a bound on how probabilistically live this thing is. So to summarize, we formalized a design that combined LMD Ghost and Casper. So this creates a full proof of stake blockchain using the LMD Ghost fork choice rule and the Casper finality gadget. We proved some safety theorems and both plausible liveness and probabilistic liveness theorems. A few disclaimers. The actual implementation has some differences from our idealized picture here. For example, there's a delay acceptance of the justification of a block. The definition of finalization is actually slightly different. And of course, they have to deal with dynamic validator sets, which is the sets of validators should be able to change. Like some people should be able to exit and some people should be able to come in. We actually prove a safety theorem even with dynamic validator sets in the Gasper paper, but I think that's a place where it would be really good to have, say, a next paper that talks about the intricacies that happen. So just a quick shout out, this was project made possible by this Camcos program at my university, which allowed me to work with all these students. And we thank the Ethereum Foundation and the Research Foundation for supporting this program. And there's a lot of other people that I'm not going to be able to all name that looked at this paper and really helped us out, and I'm really thankful for them. But in particular, I'm going to do a shout out for runtime verification because they not only gave us really helpful comments, they also did formal proof verification of our formal human proofs with CUP. So cool, thanks for listening. Yeah, sorry.
I see a question from Andrew in the chat. Andrew, did you want to elaborate or should I read?
Yeah, sure. I'm really glad to see an improvement or extension on the plausible liveness, which seems, very kind of unusual by distributed consensus protocol standards, like a weak kind of property to get. And it seems like probabilistic liveness addresses that. My question is on like what are the assumptions for the network basically, like during when the probabilistic finality occurs? Like, are you assuming that the messages are delivered according to a fixed distribution or in any order according to a worst case adversary up to some maximum delay or something else?
Cool, that's a really good question. And so I'm gonna say like this. The way I structure my proofs is to be as independent as possible, which means the only part of the proof that uses the assumption is in this first slot. And everything else is meant to be automatic after the first slot. So that makes the proof a little bit more pessimistic, but kind of also more robust. And secondly, to actually answer your question, the requirements for the first slot are you want 1/2 synchrony. And then the reason is, and then I don't make any more assumptions than that, but I kind of leave the results of the first part as black box for the second, because it's really hard to prove things outside of the first slot. That's why my proofs feel like, okay, if you can bound winning the first slot with probability R, then everything else is in terms of R.
So what you meant by 1/2
I think synchrony? Within the, so yeah, I just mean everything, you get everything at most 1/2 slot after they're written.
Okay, I think I get it.
Yeah, so there are more details. I think it's a little bit hard to talk about now, but if you email me or something, I'm really happy to dive into the
Sure, thank you.
And then I see a question from Jason, so maybe we'll just do one more and then handle any others offline.
Okay, yeah, so I actually asked this question yesterday to Gun, so sorry if you have heard about twice. But the question basically is that saying that when you try to implement these slashing conditions by a smart contract, then the slashing itself, I think, will eventually be part of the consensus. But if the consensus is compromised by misbehavior, how can we trust that slashing will be enforced, the incentive will be aligned?
The short answer is you can't. Your question is very good. And you really do need a separate analysis for that. For this paper, since we wanted to focus on safety and liveness, we kind of say, let's just assume the game theoretical incentives are in place for slashing to be kind of the right move. But I am actually working on an upcoming paper, although more about proof of custody, where we really say, is the slashing itself incentivized? And obviously something like that should be done for the beacon chain as well. But yeah, just in this paper, we just assume that part is taken care of. But I think your question is good and worth looking into.
All right, thanks.